Look up at the night sky. What do you see? A vast, glittering expanse of stars, swirling galaxies, and distant planets, all bathed in darkness. But here's the astonishing truth. There's an invisible sculptor at work behind the scenes, shaping everything you see. It's not gravity alone. It's not just the laws of physics as we know them. There's a hidden force weaving through the cosmos, bending the paths of stars, birthing new worlds, and even guiding the very fabric of space itself. That force, magnetic fields, think about that for a moment. These unseen lines of energy stretch across the universe, quietly orchestrating some of the most dramatic events in existence. From the fiery birth of stars to the violent storms on alien planets, from the delicate dance of galaxies to the mysterious signals from the depths of space, magnetic fields are the cosmic architects, pulling strings we're only just beginning to understand. And here's the wild part. Without them, the universe as we know it wouldn't exist. No stars, no planets, no life, just a cold, lifeless void. So how exactly do these invisible forces shape everything around us? That's the journey we're about to take together. Over the next 30 revelations, we'll uncover how magnetic fields twist space-time, fuel unimaginable cosmic explosions, and even hold the secrets to alien life. We'll explore how they sculpt the birth of solar systems, bend light in ways that defy logic, and create phenomena so bizarre they sound like science fiction. This isn't just a story about physics, it's a tale of cosmic wonder, of hidden forces that whisper the universe's greatest secrets to those who know how to listen. Ready to see the cosmos in a whole new light? Let's begin. Picture a swirling cloud of gas and dust in the depths of space, dark, chaotic, and seemingly lifeless. Yet hidden within that chaos lies the blueprint for a star's birth, and the architect is magnetism. When these vast cosmic clouds collapse under their own gravity, they don't just crumple randomly. Instead, they align themselves like iron filings around a magnet, tracing the invisible lines of magnetic fields that stretch across the universe. These fields act as cosmic scaffolding, guiding the gas into dense, spinning disks where gravity can finally take over and ignite the nuclear fires of a newborn star. Take the Orion Nebula, for example, a stellar nursery visible to the naked eye. What looks like a hazy smudge in the night sky is actually a frenzy of creation, where magnetic fields channel collapsing gas into tight spirals, each one a potential star in the making. Without these fields, the gas would scatter wildly, like sand tossed into the wind, and star formation would fizzle before it could begin. But magnetism brings order to the chaos, ensuring that enough material gathers in one place to reach the critical pressure needed for fusion. It's not just about gravity's pull, it's about magnetism's guiding hand. And here's something even more remarkable. These fields don't just help stars form, they shape their very spin. As the gas cloud contracts, the magnetic field lines twist and tighten, transferring energy like a cosmic spring winding up. This spin determines how planets will eventually orbit the star, setting the stage for entire solar systems. So the next time you gaze at the night sky, remember, every star you see owes its existence to the silent, invisible tug of magnetism, weaving order into the cosmos one stellar cradle at a time. Now let's zoom out from stellar nurseries to something even grander, the sprawling architecture of entire galaxies. If you've ever marveled at images of spiral galaxies like our own Milky Way, with their elegant, curving arms stretching outward, here's a mind-bending revelation. Magnetism plays a hidden role in sculpting those very shapes. What we see as glowing ribbons of stars and dust are actually tracing the contours of an invisible skeleton, a vast web of magnetic fields that permeate the galaxy, guiding its structure from within. Recent maps of the Milky Way reveal something astonishing. Colossal magnetic filaments, some stretching hundreds of light years, running parallel to the galaxy's spiral arms like cosmic reinforcement bars. These aren't random wrinkles in space, they're evidence of a dynamic interplay between gravity and magnetism. As gas and dust swirl through the galaxy, charged particles get caught in these magnetic threads, funneling material into denser lanes that eventually collapse into new stars. It's as if the galaxy has an invisible framework, a magnetic blueprint determining where its brightest features will form. But how does this actually work? Imagine a pot of boiling water. As heat makes the water rise and fall in currents, the motion creates patterns. In galaxies, magnetism does something similar. Turbulent motions of ionized gas twist and stretch magnetic fields into vast, rope-like structures. These fields then act like cosmic traffic signals, channeling the flow of material and energy. Without them, spiral arms might dissolve into chaotic blobs, and the galaxy's iconic shape could unravel. Here's where it gets even wilder. These galactic magnetic fields might solve a long-standing mystery. Spiral arms should, in theory, wind themselves tighter and tighter over time, like a spinning pinwheel slowing down. Yet many galaxies maintain their elegant structures for billions of years. Magnetic fields could be the stabilizing force, subtly resisting gravity's pull and preserving those sweeping arcs we find so mesmerizing. So when you look up at the Milky Way's faint band of light, remember, you're not just seeing stars. You're witnessing the fingerprint of an invisible force quietly holding the galaxy together. The sun may look like a serene ball of light in our sky, but beneath its glowing surface rages a storm of magnetic chaos. Every so often, that fury erupts in one of nature's most spectacular displays, a coronal mass ejection. Imagine a colossal rope of magnetic energy, twisted and strained until it finally snaps, hurling billions of tons of superheated plasma into space at millions of miles per hour. These aren't just solar tantrums, they're cosmic hurricanes capable of reshaping entire magnetic environments in their path. And when one of these storms barrels toward Earth, the results are both breathtaking and terrifying. Take the Carrington event of 1859, the most powerful solar storm ever recorded. Telegraph systems, the cutting-edge technology of the time, sparked and caught fire as invisible magnetic waves surged through their wires. Auroras, normally confined to polar skies, blazed so brightly over the Caribbean that birds began singing, mistaking the eerie glow for dawn. Today, a storm of that magnitude could plunge continents into darkness, frying power grids and crippling satellites in orbit. But here's what's truly mesmerizing. These eruptions aren't random. They're born from the sun's tangled magnetic fields, which act like rubber bands stretched to their limit. When opposing field lines collide and reconnect, they release energy equivalent to 1 billion atomic bombs in a process called magnetic reconnection. The resulting shockwaves ripple through the solar system, painting our skies with shimmering auroras as they collide with Earth's magnetic shield. Satellites orbiting Earth are the first to feel the storm's wrath. Charged particles bombard sensitive electronics, scrambling GPS signals and knocking out communications. Astronauts aboard the International Space Station take shelter in shielded compartments, while airlines reroute flights to avoid radiation spikes at high altitudes. Yet for all the disruptions, there's undeniable beauty in the aftermath, the auroras. These dancing lights are nature's own light show, as solar particles spiral down Earth's magnetic field lines and ignite the upper atmosphere in hues of green, purple, and red. Scientists now monitor the sun's magnetic tantrums around the clock, knowing that one well-aimed eruption could send us back to the pre-digital age. But beyond the danger lies a profound truth. These storms are reminders that we're tethered to a star, bound by invisible magnetic threads that connect us to the cosmos itself. Deep in the cosmos, hidden among the swirl of stars, lurk monsters so powerful they can rip reality itself apart. Not with gravity or brute force, but with pure magnetism. These are magnetars, the universe's ultimate magnets, born from the corpses of massive stars and packing a punch that defies imagination. Picture a neutron star, an object so dense a teaspoon of its material would weigh 1 billion tons, then crank its magnetic field up to 1 quadrillion times stronger than Earth. That's a magnetar, nature's most intense magnetic prison, where the laws of physics twist into something unrecognizable. Take SGR 1806-20, a magnetar located 50,000 light-years away. In 2004, it unleashed a burst of energy so violent it temporarily compressed Earth's upper atmosphere from halfway across the galaxy. For a fraction of a second, this single object outshone the entire Milky Way. But how magnetars don't just have strong magnetic fields. Their fields are so intense they can literally bend the fabric of spacetime around them, creating cracks in their crust called starquakes. When these cosmic quakes strike, the magnetar's rigid surface shudders, snapping magnetic field lines like rubber bands and releasing tsunamis of X-rays and gamma rays. Here's where it gets even stranger. These fields don't just affect the magnetar, they alter the very atoms around it. In a normal magnetic field, electrons orbit nuclei in predictable patterns. But near a magnetar, the field warps those orbits into impossible shapes, stretching atoms into thin, needle-like rods. Even the vacuum of space isn't safe. The field becomes so strong it polarizes empty space itself, creating a bizarre effect where light splits into two different paths like a cosmic mirage. Yet magnetars aren't just destructive. Their extreme environments act as laboratories for physics we can't replicate on Earth. When their magnetic fields decay, they emit steady pulses of X-rays, acting as cosmic lighthouses that help astronomers map the universe's structure. Some scientists even theorize that magnetars could be behind mysterious fast radio bursts, those fleeting, powerful signals from deep space that have puzzled researchers for years. So the next time you hear about a distant gamma ray flash or a strange radio pulse rippling through the cosmos, remember, somewhere out there, a magnetar might be flexing its magnetic muscles, reminding us that the universe holds forces far beyond anything we've witnessed on Earth. These aren't just dead stars, they're cosmic powerhouses, bending spacetime and rewriting the rules of physics with every shudder. Earth is surrounded by an invisible force field, one so powerful it deflects lethal cosmic radiation and solar storms, yet so delicate we don't even feel its presence. This is our magnetosphere, a vast magnetic bubble generated deep within the planet's molten core. Here, rivers of liquid iron twist and churn like a cosmic dynamo, creating electric currents that birth a planetary-scale magnetic field stretching thousands of miles into space. Without it, Earth would be a barren wasteland, stripped of its atmosphere by the sun's relentless solar wind. Picture the solar wind as a supersonic river of charged particles, screaming toward Earth at nearly 1,000,000 miles per hour. But as it crashes into our magnetosphere, something extraordinary happens. The particles don't slam directly into the atmosphere. They are funneled along the magnetic field lines, spiraling toward the poles in a dazzling light show we call the auroras. It's like watching water flow around a rock in a stream. The field bends the solar wind's path, shielding us from its full fury. But this shield isn't static. Hidden in ancient rocks lies evidence of a startling truth. Earth's magnetic poles have flipped repeatedly throughout history. Lava flows frozen in time reveal minerals aligned with magnetic fields pointing south instead of north, telling the story of a planet whose magnetic identity is far from permanent. These reversals don't happen overnight. They take centuries, during which the field weakens, fractures into multiple poles, and eventually restabilizes in the opposite orientation. What would happen if a reversal occurred today? Satellite communications could falter as solar radiation penetrates deeper into the atmosphere. Migratory animals, from whales to birds, might lose their natural compass. But here's the twist. Despite Hollywood's doomsday scenarios, past reversals didn't trigger mass extinctions. Life persisted, because while the field weakens, it rarely vanishes completely. The magnetosphere's dance is a reminder that even our planet's most steadfast protections are part of a grander, ever-changing cosmic rhythm. Scientists now track the magnetic field's gradual shifts with satellites like SWARM, which map its ebb and flow in real time. They've discovered something peculiar. The North Magnetic Pole is sprinting across the Arctic at unprecedented speeds, shifting dozens of miles each year. Some speculate we might be on the brink of another reversal, a planetary reset written in the silent language of magnetism. Whether it happens in our lifetime or millennia from now, one thing's certain: Earth's magnetic shield is more than a static barrier. It's a living, breathing entity as dynamic as the molten engine that fuels it. In the aftermath of a star's catastrophic death, something extraordinary happens. A natural particle accelerator, more powerful than anything humans could ever build, roars to life. When a massive star explodes as a supernova, it doesn't just vanish into oblivion. Instead, it leaves behind a tangled wreckage of gas and magnetic fields, a cosmic obstacle course where particles get flung to nearly the speed of light. These aren't just random debris, they're cosmic rays, high-energy messengers from across the universe, and their secret driver is magnetism. Take the Crab Nebula, the remnants of a supernova witnessed on Earth in the year 1054. At its heart lies a spinning neutron star, a pulsar whipping magnetic field lines around like a celestial lasso. These fields don't just sit there, they act as slingshots, grabbing charged particles and hurling them outward with unimaginable force. Imagine a surfer catching an endless wave, but instead of water, it's a tsunami of magnetic energy propelling electrons and protons to velocities so high they glow with X-rays. That's what we see in the crab's shimmering filaments, particles spiraling along magnetic pathways, their paths etched in light. But how does this acceleration actually work? Picture a rubber band stretched to its limit, storing energy until it snaps. In supernova remnants, magnetic fields behave similarly, building up tension as they twist and tangle. When they finally reconnect, they release explosive bursts of energy, kicking particles to nearly the speed of light in milliseconds. It's like a cosmic pinball machine where particles ricochet off magnetic shockwaves, gaining speed with each collision. Some of these particles escape into interstellar space, becoming the cosmic rays that bombard Earth from every direction. Here's the wild part: these rays aren't just harmless space static. They're so energetic they can penetrate spacecraft and even affect airline passengers at high altitudes. Yet they're also clues to the universe's most violent events. By studying their paths, scientists can trace them back to their origins, often to supernova remnants like the Crab. These magnetic accelerators don't just create cosmic rays, they're the universe's way of recycling energy, turning stellar death into the birth of particles that might one day spark life elsewhere. So the next time you see a supernova remnant glowing in a telescope image, remember, you're not just looking at a dead star's ghost, you're witnessing a cosmic power plant where magnetism transforms destruction into something astonishing, a natural engine that fuels the universe itself. There's a moment in nature when tension becomes too much, when something stretched to its limit finally snaps. In space, this moment isn't just dramatic, it's explosive. It's called magnetic reconnection, and it's one of the universe's most efficient energy converters. Picture two magnetic field lines running parallel like train tracks. They're under immense pressure, pushed closer and closer until, bang, they suddenly break and reconnect in an entirely new configuration. The energy released in that instant rivals millions of hydrogen bombs, and it happens in a flash so brief, we've only recently captured it in action. NASA's magnetospheric multiscale mission gave us a front-row seat to this phenomenon. Flying through Earth's magnetic field in tight formation, these satellites recorded reconnection events down to the millisecond. What they found was staggering. Particles accelerated to nearly the speed of light as magnetic energy transformed into heat and motion. It's like uncorking a champagne bottle. the built-up pressure releases all at once, sending a shockwave rippling through the surrounding plasma. This isn't just some distant cosmic curiosity. Magnetic reconnection powers the solar flares that erupt from our sun's surface, those loops of glowing plasma you see in solar telescope images. They're the aftermath of field lines snapping and reconnecting, launching superheated gas into space. When one of these eruptions heads our way, the real magic happens at Earth's poles. Charged particles from the solar wind, funneled by our planet's magnetic field, collide with the upper atmosphere in a cascade of light, the auroras. Those shimmering curtains of green and red are literally the glow of oxygen and nitrogen atoms getting zapped by reconnection-accelerated particles. But here's the twist. Reconnection isn't just destruction, it's also creation. In laboratories, scientists replicate this process to study fusion energy, hoping to harness the same mechanism that powers stars. Out in the galaxy, reconnection may explain how black holes launch jets of material across thousands of light years. Even Earth's own magnetic field, constantly pushed and pulled by the solar wind, relies on reconnection to release built-up stress without tearing apart completely. The more we learn, the clearer it becomes. This invisible process is a universal key. From the smallest lab experiments to the grandest cosmic fireworks, magnetic reconnection is the universe's way of turning tension into transformation, one explosive snap at a time. At the heart of the galaxy known as Messier 87, a monstrous black hole weighing 6.5 billion times the mass of our Sun is performing what seems like an impossible magic trick. It's not just devouring matter. It's shooting a narrow beam of superheated plasma straight into space at nearly the speed of light, stretching over 5,000 light-years. This isn't just any cosmic jet, it was the first one humanity ever photographed thanks to the Event Horizon telescope. But here's the real puzzle. How does something so chaotic as a black hole, a place where gravity is king, produce such a perfectly focused beam? The answer lies in an invisible cosmic sculptor, magnetic fields. Black holes don't just swallow everything that comes near them. Some material gets caught in a swirling disk of superheated gas called an accretion disk, spinning so fast it glows white-hot with friction. But without magnetism, this disk would be a messy, turbulent storm, flinging material in all directions. What changes the game are the magnetic field lines embedded in the disk, threads of energy that rise like whirlwinds from the chaos below. As the disk spins, these fields twist into tightly wound coils, acting like cosmic nozzles that channel some of the infalling matter away from the black hole's grasp and launch it outward in opposing jets. The sheer precision of these jets is what baffles scientists, despite originating from an environment of unimaginable violence, where gas is torn apart by tidal forces and heated to billions of degrees. The jets remain remarkably straight and narrow over thousands of light-years. That's magnetism's handiwork. The field lines act like the walls of a laser tube, keeping the plasma from fanning out into useless clouds. Without this magnetic collimation, the energy would dissipate into the void, and we'd never see those spectacular beams piercing through galaxies. But why does this matter beyond cosmic eye candy? These jets are among the most efficient engines in the universe. They pump energy into intergalactic space, heating clusters of galaxies and even suppressing star formation by stirring up galactic gas. Some researchers think they could be the reason certain galaxies stop making new stars, literally shutting down cosmic nurseries with a blast of magnetically focused energy. And here's the twist. The same process might be happening on a smaller scale all around us. Young stars, neutron stars, and even some planets like Jupiter show scaled-down versions of these jets. It seems magnetism has a favorite blueprint for turning chaos into focused power, whether around a black hole or a newborn star. So when we gaze at images of M87's jet stretching across space, we're not just seeing a black hole's outburst. We're witnessing the universe's way of sculpting raw fury into something precise, powerful, and strangely beautiful, all guided by the silent, invisible hand of magnetism. Imagine standing on a world with flowing rivers and thick air, Mars 4 billion years ago. Fast forward to today, and it's a barren desert, its atmosphere stripped away by the solar wind. What changed? The answer lies in the silent guardian Earth still has, but Mars lost, a global magnetic field. Without this invisible shield, even a planet swimming in water and brimming with air can turn to dust. Take Venus and Earth, twins in size, yet worlds apart. Venus has no magnetic field to speak of, and the Sun's relentless wind has battered its atmosphere into a suffocating, superheated mess. Meanwhile, Earth's magnetosphere acts like an umbrella in a cosmic downpour, deflecting charged particles that would otherwise scrape away our atmosphere molecule by molecule. The difference isn't just theoretical. NASA Maven orbiter watched it happen at Mars in real time, measuring how solar storms rip gas from the upper atmosphere when the planet's ancient magnetic shield failed. Here's the twist: magnetism doesn't just block solar wind. It shapes a planet's entire climate. Earth's field steers cosmic rays away, preventing them from smashing into our air and triggering chemical reactions that could destroy ozone or spawn destructive weather. On Mars, without that protection, radiation sears the surface, making life as we know it impossible. Even more fascinating, some of that lost Martian air might still be clinging to the planet, trapped in icy deposits or mineral bonds, a ghost of the atmosphere magnetism once guarded. Now look beyond our solar system. Astronomers hunting habitable exoplanets have started searching for magnetic fields indirectly, studying how worlds interact with their stars. A flicker of radio waves, a telltale glow of auroras. These could hint at an invisible shield protecting alien skies. Planets orbiting red dwarfs, often bombarded by violent stellar flares, might need magnetism even more than Earth does to preserve their atmospheres. So when we wonder why Earth thrived while Mars withered, magnetism holds the key. It's not just about having the right ingredients for life, it's about keeping them safe. As we discover more exoplanets, the presence or absence of a magnetic field might be the difference between finding a second Earth or another cosmic tombstone. Stretching across the unimaginable voids between galaxies, there's a hidden architecture to the cosmos, one so vast it makes even the grandest galactic structures seem small. Astronomers call it the cosmic web, a sprawling network of filaments where dark matter and gas form bridges between galaxy clusters. But here's the revelation that's rewriting textbooks: these filaments aren't just passive highways of matter. They're crackling with magnetic energy, threaded with fields so immense they could wrap around our entire galaxy 1,000 times over. For decades, these magnetic threads were invisible to us, their presence only hinted at by the way charged particles spiraled through intergalactic space. Then came groundbreaking observations from radio telescopes like LOFAR, peeling back the curtain on something extraordinary. When scientists mapped the faint glow of synchrotron radiation, a telltale sign of electrons whipping around magnetic fields, they found something shocking. The cosmic web wasn't just glowing in isolated patches. It was lit up like a neon sign, with magnetic fields tracing every filament, every junction, as if the universe itself was wired with invisible power lines. How does magnetism weave itself into the fabric of the cosmos on such a mind-boggling scale? The leading theory points back to the universe's infancy. In the turbulent plasma of the early cosmos, tiny seed fields, perhaps generated by quantum fluctuations or the first exploding stars, got stretched and amplified as the universe expanded. Over billions of years, gravity pulled these fields along with the gas and dark matter, aligning them into the colossal filaments we see today. It's like watching iron filings arrange themselves along the lines of a magnet, only here, the magnet is the universe's underlying structure, and the filings are entire superclusters of galaxies. But these fields aren't just cosmic decoration, they're dynamic players in the universe's evolution. Take the Abell 39 galaxy cluster, where magnetic filaments act like cosmic particle accelerators, boosting electrons to near-light speeds as they surf along the field lines. Elsewhere, these fields may regulate how gas flows into growing galaxies, controlling the birth rate of stars by either channeling fuel or putting up magnetic roadblocks. Some researchers even speculate that these vast networks could influence the trajectories of ultra-high-energy cosmic rays, those mysterious particles from deep space that occasionally slam into Earth with the force of a fastball. Perhaps most astonishing is what these magnetic threads reveal about the universe's interconnectedness. Just as neurons communicate across the brain's synapses, galaxy clusters might be linked by these magnetic channels, exchanging energy and matter across millions of light years. It's a humbling thought. The same force that guides a compass needle on Earth also stitches together the largest structures in existence, binding the cosmos in a web of invisible force. So when you look up at the night sky, remember, you're not just seeing stars, you're glimpsing the nodes of a vast magnetic tapestry, one that's been spinning its threads since the dawn of time. The sun may seem like a perfect golden orb in our sky, but peer closer through the lens of a solar telescope, and its surface reveals a hidden drama. Dark blemishes speckle its fiery face, some as large as planets, others vanishing within hours. These are sunspots, the most visible fingerprints of the sun's churning magnetic personality. Far from static scars, they're dynamic whirlpools of plasma, where tangled magnetic fields punch through the solar surface like cosmic tornadoes, cooling the gas beneath them and creating those ominous dark patches against the sun's brilliance. Watch a time lapse of the sun over weeks and you'll witness something mesmerizing. Sunspots marching across its face, clustering near the equator before fading away. This isn't random activity, it's the heartbeat of an 11-year cycle, a rhythmic dance of magnetic energy that governs everything from solar flares to Earth's auroras. During solar maximum, the sun's face becomes freckled with hundreds of spots, while solar minimum leaves it nearly blank. The cycle resets when the sun's magnetic poles flip, north becomes south and vice versa, a celestial switcheroo that's been happening like clockwork for millennia. But why 11 years? The secret lies beneath the surface. The sun doesn't rotate as a solid ball. Its equator spins faster than its poles, dragging magnetic field lines like taffy. Over time, these lines stretch, twist, and snap, erupting through the surface as sunspot pairs, one a magnetic north, the other a south. Like an overworked rubber band, the fields eventually rebound, resetting the cycle. The regularity is uncanny. Records from the 1600s, when astronomers first tracked sunspots through telescopes, show the same 11-year pattern we observe today. These spots aren't just cosmetic. When magnetic tension in a sunspot becomes too extreme, it triggers solar flares, explosions brighter than 1,000,000 atomic bombs. The largest, called X-class flares, can rip through Earth's magnetic shield, disrupting satellites and radio communications. In 1989, a flare-induced geomagnetic storm blacked out Quebec's power grid for 9 hours, leaving millions in the dark. Yet sunspots also have a quieter, more artistic side. Their magnetic fields guide charged particles into Earth's poles, painting the skies with auroras that dance in sync with the sun's restless magnetic moods. What's truly astonishing is how sunspots connect us to distant stars. Astronomers studying other suns have spotted similar star spots, some so massive they dwarf our entire solar system. On a star called V1354 Orionis, a single spot covered a quarter of its surface, causing brightness dips visible across interstellar space. These distant spots reveal a universal truth. Magnetism isn't just a solar quirk. It's a language spoken by stars across the cosmos, written in dark patches and violent flares, a reminder that even in the vastness of space, the same forces shape our local star and its far-flung siblings. Around a black hole's gravitational maw, something counterintuitive happens. Gas doesn't just plummet straight into oblivion. Instead, it swirls into a luminous, pancake-shaped vortex called an accretion disk, where particles jostle and spiral inward at nearly light speed. But here's the paradox: if gravity alone ruled this chaos, matter would vanish into the black hole in seconds. Yet some disks shine for millions of years, their material inching inward at a glacial pace. The reason: magnetic turbulence, a hidden force stirring the pot, slowing the feast, and lighting up the universe's darkest corners with its fury. Picture the disk as a cosmic hurricane where superheated gas churns in extreme conditions. Atoms are ripped apart into plasma, electrons stripped from nuclei, creating a soup of charged particles ripe for magnetic influence. As these particles orbit, they drag magnetic field lines with them, twisting them into spirals. But like overstretched rubber bands, the fields snap, reconnect, and tangle into knots of energy. This magnetic mayhem acts as a cosmic brake, transferring energy outward and creating friction that heats the disk to millions of degrees, hence its blazing glow. Without this turbulence, the disk would collapse silently into the black hole, leaving nothing to observe. The movie Interstellar gave us a hauntingly beautiful glimpse of this process. Its black hole, Gargantua, warped spacetime so severely its accretion disk stretched into a halo of light above and below the singularity, a phenomenon grounded in real physics. But what the film didn't show was the invisible scaffolding behind that luminous ring, the magnetic fields writhing like serpents beneath the surface. Recent supercomputer simulations revealed disks aren't smooth at all. They're fractal landscapes of magnetic loops and eddies where plasma rises in searing columns before crashing back down, a process called the magnetorotational instability. It's this very instability that keeps the disk alive, preventing gas from free-falling too quickly by turning its motion into heat and light. Astronomers have spotted this magnetic fingerprint in real time. When the Event Horizon Telescope captured the first image of a black hole's shadow in M87, the swirling polarization patterns in the surrounding light revealed the disk's magnetic field structure. The lines weren't chaotic, they were surprisingly organized, coiled like springs around the black hole's spin axis. This alignment suggests magnetism doesn't just stir the disk, it also launches those relativistic jets we see screaming away from the poles, funneling energy into space like a cosmic exhaust valve. What's truly mind-bending is how universal this dance appears. From stellar mass black holes to supermassive beasts like Sagittarius, a star at our galaxy's heart, the same magnetic choreography plays out across scales. Even newborn stars, with their own miniature accretion disks, exhibit similar turbulence, hinting that magnetism's role as cosmic traffic cop might be written into the fundamental laws of how matter falls onto anything with gravity. So the next time you see an artist's rendering of a black hole's glowing disk, remember, you're not just looking at hot gas, you're witnessing magnetism's masterpiece, a self-regulating engine where chaos and order collide to power the brightest phenomena in the universe. For centuries, sailors navigated Earth's oceans by reading the stars, but the next generation of explorers might chart their course using something far more subtle, the galaxy's own magnetic highways. Imagine a spacecraft surfing not on rockets or solar sails, but on the invisible latticework of magnetic fields stretching between the stars. It sounds like science fiction, yet the blueprint for this interstellar navigation system is already being written, not by us but by nature itself. Take NASA Voyager probes, humanity's farthest flung messengers. As they ventured beyond the solar wind's protective bubble, their instruments detected something astonishing. The Milky Way's magnetic field isn't a hazy backdrop, it's structured like a series of cosmic lanes, with sudden shifts in direction and intensity marking the boundaries between interstellar regions. These magnetic road signs could one day guide future missions, offering natural reference points in the featureless void between stars. The key lies in a phenomenon called magnetic reconnection, the same process that powers solar flares. A spacecraft could theoretically hitch a ride on these field lines, using controlled bursts of plasma to trigger reconnection events that propel it forward, like a surfer catching waves. Researchers at Princeton's Plasma Physics Lab have already simulated miniature versions of this in the lab, showing how plasma thrusters could push off magnetic fields to gain momentum without carrying vast amounts of fuel. But the real magic happens when you combine this with another cosmic quirk. Many interstellar magnetic fields are twisted into helical spirals by the galaxy's rotation. These spirals could act like galactic rivers, with spacecraft riding the currents by adjusting their trajectory to match the field's pitch, a technique dubbed magnetic sailing. Picture a futuristic probe unfurling superconducting coils to interact with the surrounding fields, turning the galaxy's magnetism into an endless propulsion system. Challenges remain, of course. Interstellar fields are 1,000,000 times weaker than Earth's, requiring impossibly sensitive equipment unless we amplify them. Some designs propose creating artificial magnetospheres around ships, effectively inflating local fields to usable strengths. Others suggest tapping into cosmic rays, whose paths trace the very magnetic highways we'd want to follow. Yet the most tantalizing possibility isn't just travel, it's communication. Magnetic fields permeate the galaxy nearly instantaneously, unlike light-speed radio signals. A network of magnetically sensitive probes could theoretically relay messages across vast distances by detecting field fluctuations, creating an interstellar internet woven into the fabric of space itself. So while our first starships may still rely on conventional propulsion, the future of exploration could lie in reading the galaxy's hidden magnetic map, a roadmap written in the language of forces that shape the universe itself. Deep in the frigid voids between stars, where temperatures hover just a few degrees above absolute zero, an extraordinary chemical ballet unfolds, one guided by an unseen choreographer. Giant molecular clouds, those sprawling cosmic nurseries filled with gas and dust, might seem like barren wastelands, yet within their icy grains and turbulent flows, magnetic fields are quietly assembling the molecular building blocks of life itself. Take the famous Orion Molecular Cloud Complex, a star-forming region just 1,500 light-years away. Radio telescopes have detected over 200 different molecules here, from simple water and carbon monoxide to complex organic compounds like methanol and even glycine, the simplest amino acid. How do these intricate molecules form in an environment where atoms should be too sparse and cold to react? The answer lies in magnetism's subtle influence. Under normal conditions, gas particles in these clouds would drift aimlessly, rarely colliding with enough energy to bond. But magnetic fields change the game. They align dust grains like microscopic compass needles, creating a latticework of surfaces where atoms can stick and migrate. As these grains spin driven by magnetic torques, they act as tiny chemistry labs, exposing trapped molecules to ultraviolet light from nearby stars. This triggers reactions that would never occur in open space, gradually building more complex structures. The proof is in the polarization. When astronomers map the orientation of light waves from these clouds, they find telltale patterns revealing magnetic fields threading through the densest clumps. These fields don't just guide the gas, they shield delicate molecular chains from destructive radiation, allowing them to grow. Some simulations suggest that without this magnetic protection, complex organic molecules would be ripped apart almost as quickly as they form. Perhaps most tantalizing is what this means for life's origins. The Rosetta mission found amino acids on Comet 67P, while meteorites like Murchison contain thousands of organic compounds. Now we're discovering these same molecules in stellar nurseries across the galaxy. It's as if magnetism has been weaving life's ingredients into the fabric of star systems from the very beginning, a cosmic assembly line running silently in the dark. From the sugar molecules in the Sagittarius B2 cloud to the ethanol rivers of the G3 4.300 star-forming region, the message is clear: the universe isn't just making stars and planets. It's brewing chemistry intricate enough to one day spark life, all under the guiding hand of invisible magnetic fields. In the constellation Vulpecula, 1,000 light-years from Earth, a celestial metronome ticks with impossible precision 30 times every second. This is the Crab pulsar, the spinning corpse of a star that exploded in 1054, now blasting beams of radiation into space like a cosmic lighthouse. But what makes this dead star pulse with such perfect rhythm? The answer is magnetism twisted, amplified, and focused into nature's most precise timekeeping device. When Jocelyn Bell Burnell first detected these rhythmic radio pulses in 1967, the signal was so unnervingly regular that her team jokingly labeled it LGM-1, a little green men. The idea of an alien beacon captured imaginations, but the truth proved even more extraordinary. Pulsars aren't extraterrestrial signals, they're neutron stars, city-sized stellar remnants spinning so fast their surfaces move at nearly light speed. What transforms them into cosmic lighthouses is their crushing magnetic fields, which channel radiation into narrow beams shooting from their magnetic poles. Like a spinning fire hose, these beams sweep across space, and when one happens to point at Earth, we detect a pulse, sometimes hundreds per second. The precision of these pulses defies belief. Some pulsars, like PSR J0437-4715, keep time better than atomic clocks, their rotations slowing by just 1 second every 300 million years. This stability comes from their monstrous magnetic fields, trillions of times stronger than Earth's, which act like cosmic gyroscopes, stabilizing their spin against external forces. But there's a catch: the beams don't align perfectly with the rotation axis. Instead, they're offset, creating that iconic lighthouse effect as the star whirls. What's truly astonishing is how these magnetic lighthouses serve as universal navigation tools. NASA Voyager probes carry pulsar maps on their golden records, with directions to Earth based on the unique pulse patterns of nearby neutron stars. Future interstellar travelers might triangulate their position using these cosmic beacons, their steady flashes cutting through the dark like mile markers on a galactic highway. Yet pulsars aren't immortal. Over millennia, their magnetic fields gradually decay, slowing their spins until the pulses fade into silence. Some, like the 1800 pulses per second monster PSR J1748-2446 AD, are destined to vanish faster, their furious energy expenditure bleeding them dry. But for now, they remain nature's perfect timepieces, their rhythmic ticks echoing across the cosmos, written in the language of magnetism. Deep beneath the ocean floor, in places where sunlight never reaches and the pressure could crush a submarine, life thrives in ways that defy imagination. Here, in the cracks of hydrothermal vents and buried in ancient sediments, microscopic organisms don't just survive, they navigate using an invisible force we can barely perceive. These are magnetotactic bacteria, Earth's simplest yet most astonishing magnetic pioneers, and they might hold clues to how life could flourish in the cosmos's harshest corners. Each of these bacteria is a self-contained compass, manufacturing tiny crystals of magnetite, the same mineral birds use to sense Earth's magnetic field. But unlike birds, these microbes don't just detect magnetism, they build it into their very structure. Chains of nanoscale magnets align like microscopic arrows, steering the bacteria along magnetic field lines as effortlessly as a train on a track. For them, magnetism isn't just helpful, it's essential. In the oxygen-free depths where they thrive, following magnetic field lines downward leads to safety, while straying upward could mean poisoning. It's a survival strategy so elegant, it's evolved independently multiple times across the planet. Now imagine this principle scaled up to alien worlds. On a planet with a weak or erratic magnetic field, life might evolve to harness local magnetism in even more creative ways. Picture extremophiles on a tidally locked exoplanet, where one side forever faces its star and the other drowns in eternal night. Magnetic sensing could guide organisms toward the twilight zone, the narrow band of habitable real estate between scorching heat and frozen darkness. Or consider life forms floating in the subsurface oceans of icy moons like Europa, where global magnetic fields generated by Jupiter's tidal forces might create navigational highways beneath miles of ice. The possibilities extend beyond mere orientation. Some researchers speculate that advanced extraterrestrial life could use magnetoception for communication, encoding messages in magnetic pulses, much like whales use sound waves across ocean basins. On a planet with constant electrical storms or auroras, such a system would be far more reliable than vision or hearing. Even more intriguing, if life exists on rogue planets adrift between stars, devoid of sunlight, magnetic fields might be their only consistent reference point in an otherwise featureless void. Back on Earth, the implications are just as profound. Magnetotactic bacteria leave behind magnetic signatures in sedimentary rocks, clues that could help us identify ancient life, not just here but on Mars or other worlds. The rover Perseverance found magnetite-rich rocks in Jezero crater, and while it hasn't spotted bacteria fossils yet, the building blocks are there. If magnetism guides life in Earth's extremes, why not elsewhere? So while we scour exoplanets for oxygen or methane as signs of life, we might be missing a quieter, more universal language, one written in magnetic fields. From microbes aligning like living compass needles to hypothetical alien ecosystems tuned to the hum of planetary magnetism, the universe could be buzzing with life we've barely learned to detect. After all, if something as simple as a bacterium can master this force, who's to say what else might be out there, navigating the cosmos along roads we're only beginning to map? Galaxies aren't just islands of stars, they're breathing giants, exhaling colossal winds that shape their own destiny. These aren't gentle breezes, but supersonic rivers of gas, charged particles, and cosmic dust, roaring outward at millions of miles per hour. And what controls these titanic outflows? Magnetic fields woven through the chaos like invisible reins, directing where the wind blows and how it sculpts the galaxy around it. Take the iconic Hubble image of galaxy Messier 82, a starburst galaxy frenetically birthing new stars. What should be a smooth disk is instead fractured, with enormous bubbles of gas erupting from its core. These aren't random explosions, they're the work of galactic winds, channeled and accelerated by magnetic fields threading through the chaos. As newborn stars ignite, their radiation and supernova blast gas outward, but without magnetism, this material would spray in all directions like a shattered hose. Instead, the fields collimate these outflows into focused jets and vast, expanding shells, punching holes in the surrounding gas that astronomers call superbubbles. But here's the twist: these winds aren't just destruction, they're regulation. A galaxy without winds would burn through its gas too quickly, spawning stars in a brief, fiery frenzy before starving into silence. Magnetic fields moderate this process. Like a cosmic thermostat, they help steer the winds to specific altitudes, where they cool and eventually rain back down in a process called galactic recycling. The Southern Pinwheel Galaxy, M83, showcases this perfectly. Its magnetic filaments guide ejected material into graceful arcs that eventually fall back, fueling future generations of stars. The real magic happens in the circumgalactic medium, the halo of diffuse gas surrounding galaxies. Hubble's ultraviolet eyes have spotted strange, glowing structures here, like soap bubbles floating in space. These are the fingerprints of ancient winds, their shapes preserved by magnetic pressure. In the Leo cluster, some of these bubbles stretch for hundreds of thousands of light years, their surfaces shimmering with synchrotron radiation, a telltale sign of electrons spiraling around magnetic field lines. What's astonishing is how these fields act as cosmic architects. Simulations show that without magnetism, galactic winds would stall prematurely, their energy dissipating into the void. But when magnetic fields are present, they create turbulent scaffolds that keep the winds coherent over vast distances. It's like comparing a whisper to a shout. The fields amplify the galaxy's voice, allowing it to influence its surroundings far beyond what gravity alone could achieve. So when you see those stunning Hubble portraits of galaxies wreathed in glowing halos, you're not just looking at pretty gas clouds. You're witnessing a dynamic balancing act, one where magnetic fields govern how galaxies grow, how they breathe, and ultimately how they write their own fate across the cosmos. When the universe was less than a second old, it underwent a growth spurt so violent it defies comprehension: cosmic inflation. A trillionth of a trillionth of a trillionth of a second, when space itself expanded faster than light. This explosive moment stretched quantum fluctuations into cosmic scale wrinkles, seeding the galaxies and clusters we see today. But hidden in this story is a tantalizing possibility. Primordial magnetic fields, forged in that unimaginable infancy, might have left their fingerprints on the oldest light in existence, the cosmic microwave background. The Planck satellite, humanity's most detailed map of this ancient afterglow, revealed something curious. Embedded in its temperature, fluctuations are faint, swirling patterns called B modes, subtle spirals that can't be explained by density variations alone. Theorists now speculate these could be the echoes of magnetic fields present at the universe's birth, stretched to cosmic proportions during inflation. Imagine a toddler's scribble magnified to the size of a continent. That's what inflation might have done to these primordial magnetic seeds, imprinting their structure onto the fabric of spacetime itself. What's wild is how delicate this evidence is. The signal, if it exists, is buried under noise 100 times stronger, like trying to hear a whisper in a hurricane. Yet the hunt continues because the payoff would rewrite physics. Most models assume magnetic fields arose later from the turbulent motions of ionized gas in galaxies. But if Planck's B modes confirm their primordial origin, it means magnetism isn't just a byproduct of cosmic evolution. It's a fundamental feature baked into the universe from its first breath. Here's where it gets mind-bending. These fields wouldn't have been like the neatly ordered ones around magnets today. They'd have been chaotic, fractal-like webs threaded through the seething plasma of the early cosmos. As inflation stretched them, they might have twisted space-time itself, creating gravitational waves that could someday be detected by observatories like LISA. It's a cosmic detective story where the clues are written in the polarization of microwaves, and the suspect is a force that predates stars, galaxies, even matter as we know it. The implications ripple outward. If primordial magnetism shaped the CMB, it could explain why galaxy clusters today are threaded with coherent magnetic fields spanning millions of light-years, structures too vast to have grown from local processes alone. Some researchers even propose these fields might have nudged dark matter into its current distribution, subtly guiding where galaxies would eventually form. So when you see those rainbow-hued Planck maps, remember, you're not just looking at a baby picture of the universe. You're glimpsing the possible shadow of magnetism's first act, an invisible hand that helped sculpt everything from the largest cosmic structures to the light that fills the void between them. And if future telescopes catch that whisper definitively, it'll prove that magnetism isn't just part of the universe's story. It was there at the very first chapter. Rising from the sun's seething surface like fiery bridges between worlds, solar prominences are some of the most breathtaking structures in our solar system, and they're sculpted entirely by magnetism. These colossal loops of plasma can stretch over 100,000 miles, dwarfing Earth itself, yet they float effortlessly above the sun's surface, defying gravity's pull. What keeps them suspended? The answer lies in the intricate dance between superheated gas and the sun's labyrinth of magnetic fields. During a total solar eclipse, when the moon briefly blots out the sun's blinding face, these prominences reveal themselves in crimson glory. tendrils of ionized hydrogen glowing against the darkened sky. But they're more than just cosmic eye candy. Each loop traces the path of a magnetic field line, its plasma particles spiraling along invisible rails like beads on a wire. The sheer scale is staggering. A single prominence might contain enough material to wrap around Earth 50 times, all held aloft by magnetic tension balancing the sun's crushing gravity. What's fascinating is how these structures evolve. Some prominences, called quiescent, linger for weeks or even months, their plasma flowing in slow-motion rivers. Others erupt violently, hurling billions of tons of charged particles into space as part of coronal mass ejections. The difference comes down to magnetic stability. When field lines twist too tightly, they snap like overstretched rubber bands, catapulting the prominence's material outward at speeds exceeding 4.5 million miles per hour. These eruptions can trigger geomagnetic storms on Earth, sparking auroras that paint the poles in otherworldly hues while threatening satellites and power grids. The best-studied prominence in history might be the one observed during the solar eclipse of 1868. Astronomers using newly invented spectroscopes identified it as hydrogen gas, marking the first time an element was discovered outside Earth. Today, spacecraft like NASA's Solar Dynamics Observatory watch prominences in ultraviolet light, revealing how their magnetic cages trap and channel plasma. Some exhibit bizarre behaviors like hedgerow prominences with vertical spikes or filament channels that snake across the sun's face like dark scars. But here's the real wonder: prominences aren't unique to our sun. The Hubble Space Telescope has spotted them on other stars, red giants, dwarfs, even binary systems where magnetic interplay creates loops stretching between two stars. They're a universal language of plasma and magnetism, written across the cosmos in arcs of glowing gas. So the next time you see an eclipse image crowned with those crimson flames, remember, you're glimpsing a force that shapes not just our solar system, but the very fabric of stellar evolution. Every magnet you've ever held, from a simple fridge magnet to the powerful neodymium ones, has two poles, a north and a south. Break it in half and you don't isolate a single pole. You just get two smaller magnets, each with their own north and south. This duality seems written into the universe's laws, except for one radical idea that could shatter everything we know. What if single-pole magnets called magnetic monopoles actually exist? The implications would be staggering, rewriting not just physics textbooks but the entire cosmic story. Back in 1931, physicist Paul Dirac made a startling prediction. His equations suggested that if even one magnetic monopole existed in the universe, it would explain why electric charge comes in fixed, indivisible units. It was an elegant idea, like finding a missing puzzle piece that suddenly makes the whole picture clear. But despite decades of searching, from deep underground labs to cosmic ray detectors, monopoles have remained frustratingly elusive. That hasn't stopped scientists from hunting. Experiments like MOEDL at CERN are designed to catch these hypothetical particles in action. Imagine a detector filled with special materials that would trap a monopole like flypaper, leaving unmistakable tracks as it passes through. Other searchers scan ancient minerals, theorizing that monopoles from the early universe might have left scars in rocks as they zipped through Earth's crust. Here's why the search matters. If monopoles exist, they could be relics from the universe's first moments, frozen into existence during cosmic inflation. Some theories suggest they might even have seeded the formation of cosmic structures, dark matter's invisible scaffolding. Others propose that monopoles could carry unimaginable energy, making them potential power sources for civilizations far more advanced than ours. And then there's the strangest possibility of all. If monopoles are out there but have simply evaded detection, it might mean they're hiding in plain sight, woven into the fabric of space itself, detectable only through their ghostly influence on other particles. Whether they are waiting to be found or forever beyond our grasp, one thing's certain: the hunt for magnetic monopoles isn't just about particles. It's about uncovering a deeper layer of reality, one that might hold the key to mysteries we haven't even dreamed of yet. Dark matter has long been the universe's most frustrating enigma, an invisible substance outweighing normal matter 5 to 1, yet refusing to interact with light or magnets as we know them. But what if we've been missing a hidden magnetic hand in the dark? Recent observations of spinning galaxies reveal a peculiar pattern. Their rotation curves, long considered proof of dark matter's gravitational grip, also show strange alignments with large-scale magnetic fields. It's as if the invisible scaffolding of the cosmos isn't just bending space, it might be humming with magnetic energy we can't yet detect. Take the galaxy NGC 26-8, a spiral like our Milky Way. Its outer stars whiz around the core far faster than visible matter alone can explain classic dark matter behavior. Yet when astronomers mapped its magnetic field using radio telescopes, they found the field lines weren't chaotic. They traced the galaxy's rotation almost perfectly, as if some unseen force were orchestrating both the dark matter halo and the magnetic dance. Coincidence? Maybe, but multiply that finding across dozens of galaxies in the Chang'e survey, and a tantalizing thread emerges. Where dark matter dominates, magnetic fields often follow suit. Theories abound. One radical idea suggests dark matter particles could carry a faint electromagnetic charge, allowing them to generate ultra-weak magnetic fields over cosmic timescales. Another proposes that dark matter interacts with regular magnetism through an unknown fifth force, a cosmic mediator that subtly twists magnetic fields into alignment with dark matter's distribution. The most mind-bending possibility: that dark matter itself is a magnetic illusion, with what we perceive as invisible mass actually being the gravitational ripple effect of primordial magnetic fields woven into spacetime during the Big Bang. The evidence is still circumstantial, like finding footprints but no creature. Yet instruments like the Square Kilometre Array radio telescope may soon change that. By mapping galaxy magnetism in unprecedented detail, it could reveal whether these alignments are cosmic flukes or the first clues to dark matter's true nature. Until then, the mystery lingers. Is the universe's missing mass quietly pulling strings through magnetism we can't yet see, or are we glimpsing an entirely new chapter in physics? Either way, the answer could rewrite not just how galaxies spin, but what binds the cosmos together at its deepest level. Earth's dancing auroras might steal the spotlight, but step outside our planet's magnetic embrace, and you'll find light shows that make ours look like a dim nightlight. Take Jupiter, where the auroras don't just flicker, they rage with enough energy to power human civilization for centuries. When NASA Juno spacecraft first trained its instruments on Jupiter's poles, it found auroras wider than Earth itself, pulsing with X-rays and glowing 5 times hotter than the planet's volcanic moon, Io. These aren't just pretty lights, they're the aftermath of a cosmic tug-of-war. Jupiter's magnetic field, 20,000 times stronger than Earth's, grabs charged particles from its surroundings, some flung from Io's sulfurous volcanoes, others siphoned from the solar wind, and hurls them into the atmosphere at nearly light speed. The result: ultraviolet storms so bright they'd be visible to the naked eye if we could survive the radiation. But Jupiter isn't the only oddity in our solar system's auroral gallery. Uranus, the ice giant spinning on its side, flaunts auroras that defy all expectations. While Earth's magnetic poles roughly align with our geographic ones, Uranus' field is tilted 60 degrees off its axis, like a compass pointing toward the horizon instead of north. When Voyager 2 flew past in 1986, it detected auroras not in neat rings around the poles as on Earth or Jupiter, but in tangled, shifting clumps. Scientists now think Uranus' lopsided magnetic field, coupled with its bizarre 98-degree axial tilt, creates a celestial disco ball effect. As the planet's magnetic poles wobble wildly during its 84-year orbit, charged particles spiral along unpredictable paths, igniting auroras that flicker on and off like a broken neon sign. The real shocker came when Hubble spotted ultraviolet auroras on Uranus decades after Voyager's visit, this time not near the poles at all, but closer to the equator. It's as if the planet's magnetic field is so tangled it can't decide where to put its light show. And then there's the strangest twist. Uranus auroras sometimes glow brighter when the solar wind dies down, the opposite of what happens on Earth. It's a reminder that magnetism doesn't play by universal rules. It sculpts each planet's sky in ways as unique as fingerprints. From Jupiter's searing X-ray storms to Uranus' drunkenly swaying lights, these extraterrestrial auroras reveal something fundamental. A planet's magnetic personality shapes not just its weather or radiation belts, but its very glow. As Juno continues to unravel Jupiter's secrets and future probes take aim at Uranus, one thing's certain: the universe has far more dazzling light shows in store than anything we've witnessed at home. So next time you gaze at the northern lights, remember, somewhere out there, a gas giant is painting its skies with magnetic fury on a scale we can barely imagine. Billions of light-years away, quasars blaze with the brightness of 1 trillion stars. Their light so intense it outshines entire galaxies. But hidden within that brilliant glare lies a subtle fingerprint of the universe's infancy, etched in the way their light waves twist and align. This phenomenon, called polarization, transforms these cosmic beacons into probes for something far more elusive: the primordial magnetic fields that shaped the cosmos just moments after the Big Bang. When light travels through space, its electric and magnetic fields normally vibrate in all directions. But when that light passes through magnetized plasma, like the scorching gas swirling around a quasar, those waves get organized. Some orientations get filtered out, leaving the light preferentially vibrating in one plane. It's similar to how polarized sunglasses cut glare by only allowing vertically aligned light waves through, except here, nature itself is the filter. By measuring this subtle alignment in quasar light, astronomers can trace invisible magnetic fields across billions of light-years, mapping structures that existed when the universe was a fraction of its current age. The key to decoding this cosmic signal lies in simulations. Supercomputers like those at NASA's Ames Research Center recreate how quasar light bends and twists as it journeys through magnetized voids. One stunning simulation shows a quasar's light initially unpolarized passing through a galaxy cluster threaded with magnetic filaments. The result: a swirling pattern of polarization that matches actual observations from telescopes like the Very Large Array. These virtual experiments reveal something astonishing. The magnetic fields imprinted on quasar light aren't random. They bear the scars of ancient turbulence from when galaxies were just beginning to form, like cosmic fossils preserved in light. Some of the most compelling evidence comes from quasars observed when the universe was barely 1 billion years old. Their polarized light shows magnetic fields already fully formed and surprisingly strong, far too developed to have grown gradually. This suggests magnetism might be primordial, woven into the fabric of space during the universe's first moments. If confirmed, it would mean magnetic fields aren't just accidental byproducts of stars and galaxies. They're fundamental architects shaping cosmic structure from the very beginning. What's even more remarkable is how these measurements sync with another cosmic clue: the polarized afterglow of the Big Bang itself. The same large-scale magnetic patterns seen in quasars appear subtly imprinted on the cosmic microwave background, hinting at a connection between the universe's birth and its adolescence. It's as if magnetism left its signature at both the starting line and the marathon's midpoint, giving us two snapshots of an invisible force guiding cosmic evolution. As next-generation telescopes like the Square Kilometre Array come online, their unprecedented sensitivity to polarized light will turn quasars into even sharper probes. We might soon trace magnetic fields back to the cosmic dark ages before the first stars flickered to life. Until then, every polarized photon from these distant beacons carries a message, one written in the secret language of magnetism, waiting to reveal how the universe went from formless plasma to the structured cosmos we call home. When a massive star reaches the end of its life in a supernova explosion, it doesn't just vanish, it carves out a cosmic cavity in the interstellar medium, leaving behind a magnetized monument to its destruction. These colossal structures, known as superbubbles, can span hundreds of light years, their walls lined with twisted magnetic fields and shock waves rippling through space like echoes of stellar thunder. Our own solar system floats inside one of these cavities, the local bubble, a region of sparse, hot gas surrounded by a shell of denser material, all shaped by the ghosts of long-dead stars. The creation of a superbubble starts with a domino effect of supernova. In regions where stars form in clusters, massive stars live fast and die young. When one explodes, its shockwave sweeps up surrounding gas and dust, compressing it into a shell laced with magnetic fields amplified by the blast. As neighboring stars erupt in sequence over millions of years, their combined energy inflates the bubble further, like a cosmic balloon expanding into the galaxy. The local bubble, for instance, was likely sculpted by around 20 supernovae that detonated within a nearby stellar nursery called the Scorpius-Centaurus Association, starting roughly 14 million years ago. Today, we drift near its center, immersed in a diffuse plasma about 1,000,000 degrees Kelvin, 10 times hotter than the Sun's surface. What makes these bubbles truly remarkable is their magnetic scaffolding. Observations from radio telescopes reveal that superbubble walls aren't just piles of debris, they're structured by intricate magnetic filaments, some stretching dozens of light years. These fields act like cosmic reinforcement bars, holding the bubble's shape against external pressure while trapping high-energy particles inside. The result: a natural particle accelerator. Electrons spiral along these field lines at nearly light speed, emitting synchrotron radiation that paints the bubble's edges in faint radio waves. The local bubble's influence is literally all around us. Earth's position inside this cavity affects how we perceive the galaxy. With less dust and gas to block our view, telescopes can peer farther into interstellar space in certain directions, while the bubble's hot, magnetized plasma deflects some lower-energy cosmic rays. Some scientists even speculate that the bubble's expansion could have influenced Earth's climate in the past by altering the flux of cosmic rays reaching our atmosphere, a controversial but tantalizing idea linking stellar death to planetary evolution. But the local bubble is just one of many. The Orion-Eridanus superbubble, visible to the naked eye as a vast, faint loop in the winter sky, spans over 1,000 light-years and glows with the energy of hundreds of supernovae. Its magnetic fields are so strong they've been mapped using the polarization of starlight passing through it. Then there's the N44 superbubble in the Large Magellanic Cloud, where a central cluster of young stars pumps energy into the structure, keeping it inflated like a celestial furnace. Each of these bubbles is a dynamic ecosystem where magnetic fields mediate the flow of energy between stars and the interstellar medium. Superbubbles don't last forever, though. Over tens of millions of years, they either burst, blowing their material into the galactic halo, or stall and collapse, seeding new generations of stars with their magnetized debris. The local bubble is already slowing down, its expansion gradually being resisted by the surrounding interstellar medium. One day, it will vanish entirely, leaving only subtle traces in the chemical and magnetic fingerprints of future gas clouds. But for now, it serves as a reminder that even the emptiest-looking voids in space are sculpted by forces as fierce as they are invisible, where stellar death gives birth to magnetized islands, and we, for a fleeting cosmic moment, float in the aftermath. Somewhere in the vast emptiness between galaxies, an invisible bullet races through the cosmos, a single subatomic particle packing the kinetic energy of a fastball, screaming toward Earth at nearly the speed of light. This isn't just any cosmic ray. It's the infamous "Oh my God" particle detected over Utah in 1991 with energy levels so extreme, physicists initially doubted their instruments. How does something smaller than an atom carry the punch of a major league pitch? And more importantly, how did it traverse billions of light years without scattering into oblivion? The answer lies in the universe's hidden magnetic highways, a sprawling network of fields that steer these cosmic bullets across intergalactic space like celestial rails. When the "Oh my God" particle slammed into Earth's atmosphere, it unleashed a shower of secondary particles so intense, detectors at the University of Utah's Fly's Eye experiment recorded it as the most energetic event ever observed. Its energy, a staggering 300 exaelectron-volts, millions of times more powerful than anything produced in human-made colliders. But here's the puzzle. Based on known physics, such a particle should have lost energy long before reaching us, bouncing off cosmic microwave background photons like a stone skipping across a pond. Unless, of course, it had help navigating twisting along magnetic field lines threaded through the voids between galaxies. These extragalactic fields are unimaginably weak, a billion times fainter than Earth's, but they're not insignificant. Spanning millions of light years, they form a labyrinthine web that gently bends the paths of charged particles. Simulations show that without this guidance, ultra-high-energy cosmic rays would spiral aimlessly, their origins forever masked by their chaotic journeys. Instead, when researchers trace the "Oh my God" particle's probable path backward, it points toward the Virgo supercluster's outskirts, where magnetic filaments may have funneled it toward us like a cosmic shotgun blast. The real mystery deepens when we consider what could even produce such a particle. No known astrophysical process, not supermassive black holes, colliding galaxies, or even gamma-ray bursts fully explains energies this extreme. Some theorists speculate these rays might be the debris of cosmic strings, hypothetical defects in space-time left over from the Big Bang. Others suggest they're the fallout from super-efficient particle accelerators hidden in active galactic nuclei, where magnetic reconnection events dwarf anything in our solar system. Whatever their source, one thing's certain: these particles are messengers from the universe's most violent corners, and their journeys are written in the language of magnetism. As observatories like the Pierre Auger Array in Argentina scan the skies for more "Oh my God" events, each detection adds another clue to the invisible magnetic map that spans the cosmos. The next time one of these cosmic bullets strikes, it might carry more than just raw energy. It could reveal the hidden architecture of the universe itself, one magnetic twist at a time. Every 11 years, the Sun quietly performs a cosmic about-face. Its magnetic poles flip, north becoming south and vice versa. This isn't just a stellar curiosity, it's a planetary game-changer. During these solar transitions, the Sun's magnetic field weakens, leaving Earth more exposed to cosmic rays and solar storms. The effects ripple across our planet, from disruptions in satellite communications to subtle but measurable shifts in global climate patterns. History offers stark reminders of the Sun's influence. Between 1645 and 1715, a period known as the Maunder Minimum, sunspots virtually disappeared, a sign of unusually low solar activity. Coinciding with this quiet phase, Europe and North America plunged into the Little Ice Age. Frost fares sprouted on the frozen Thames, glaciers advanced, and crop failures triggered famines. While the exact link between solar magnetism and climate remains debated, tree rings and ice cores tell a compelling story. When the Sun's magnetic heartbeat falters, Earth's thermostat often dips. Fast forward to the modern era, and the stakes are higher than ever. During solar maximum, the peak of magnetic turmoil, explosions like the March 1989 geomagnetic storm demonstrate the Sun's disruptive power. A coronal mass ejection slammed into Earth's magnetosphere, inducing currents so strong they overloaded Quebec's power grid. leaving 6 million people in darkness for 9 hours. Airlines rerouted polar flights to avoid radiation spikes, while satellites tumbled out of control, their orientation systems scrambled by charged particles. But the sun's magnetic flip doesn't just break things, it also creates auroras typically confined to polar latitudes, surge toward the equator during solar maximum. In 1859, the infamous Carrington event painted skies crimson as far south as Cuba, with telegraph operators reporting sparks leaping from their equipment. Today, solar physicists monitor these magnetic upheavals with satellites like NAS, a solar dynamics observatory, watching for telltale signs of brewing storms. The most puzzling impact might be on Earth's clouds. Some studies suggest cosmic rays normally deflected by the sun's strong magnetic field seed more low-level clouds when solar activity wanes. Satellites like the Cloud Aerosol LiDAR and Infrared Pathfinder satellite observations mission have detected slight increases in cloud cover during solar minima, hinting at a delicate solar climate dance orchestrated by magnetism. Yet for all the chaos, there's beauty in this cycle. The same magnetic forces that threaten our technology also shield life from interstellar radiation, sculpt Earth's climate rhythms, and paint our skies with otherworldly light. As the sun approaches its next polar reversal in 2025, scientists brace for both disruption and discovery, reminding us that we're tethered to a star whose invisible forces shape every aspect of our world. Neutrinos are the universe's ultimate ghosts. Trillions pass through your body every second, drifting effortlessly through planets and stars as if they weren't even there. These nearly massless particles rarely interact with matter, making them notoriously difficult to detect. But now, scientists have uncovered a startling twist. These silent cosmic wanderers might be whispering secrets about the magnetic fields of galaxies billions of light-years away. At the Ice Cube Neutrino Observatory in Antarctica, researchers made an unexpected discovery. Buried deep in the ice, their sensors detected high-energy neutrinos arriving from distant galaxies, but not randomly. Some appeared to align in ways that mirrored the large-scale magnetic fields threading through space. It was as if these elusive particles had subtly imprinted the invisible architecture of their cosmic journeys onto their paths, like compass needles pointing back to their origins. How could particles with no electric charge carry magnetic information? The answer lies in neutrino oscillations, the bizarre quantum phenomenon where neutrinos switch between 3 different flavors as they travel. When neutrinos pass through regions of strong magnetic fields, those fields can influence the oscillation process, leaving a faint but detectable pattern in the particle's behavior upon arrival. It's not a direct interaction, more like a cosmic echo, where the presence of magnetism subtly reshapes the probabilities of which flavors survive the trip. One of the most compelling examples comes from Blazar's supermassive black holes firing jets of particles directly at Earth. When neutrinos from these galactic monsters reach Ice Cube, their flavor ratios sometimes skew in ways that match the polarized light emitted by the same jets, a telltale sign of magnetic field influence. It's as if the neutrinos and photons, 2 seemingly unrelated messengers, are both carrying fragments of the same magnetic story across the cosmos. This discovery opens an entirely new window into the universe's hidden magnetic landscape. Unlike light, which gets absorbed or scattered by dust and gas, neutrinos travel unimpeded from the farthest corners of space. By studying their oscillations, we might one day map the magnetic fields inside galaxy clusters, the voids between superclusters, or even the turbulent regions near black holes, places light alone can't reveal. But the real revolution lies in what this means for cosmology. If neutrinos truly encode magnetic fingerprints, they could help solve one of astrophysics' biggest mysteries, where cosmic magnetism came from in the first place. Are these fields primordial, woven into the universe during its first moments, or did they grow later, forged by the turbulent motions of galactic gas? Neutrino observatories of the future, like the planned Pacific Ocean neutrino experiment, could trace these fields back to their infancy, offering clues about the fundamental forces that shaped everything we see. So the next time you hear about a ghost particle detection, remember, they're not just cosmic oddities. They might be the universe's stealthy cartographers, mapping the invisible magnetic highways that guide galaxies, shape star formation, and perhaps even hold the key to understanding the cosmos on its grandest scales. Wormholes have long tantalized physicists and sci-fi fans alike, hypothetical tunnels through space-time that could connect distant corners of the universe in an instant. But there's a glaring problem. According to general relativity, these cosmic shortcuts would collapse the moment anything tries to pass through, crushed by their own gravitational forces. Unless, that is, something exotic intervenes to prop them open. Enter magnetism, not as we know it, but in its most extreme theoretical form. Imagine threading a wormhole with ultra-strong magnetic fields, trillions of times more powerful than anything in nature. Some models suggest these fields could generate negative energy densities, a bizarre quantum effect where the vacuum of space itself pushes outward rather than pulling inward. This anti-gravitational pressure might counteract a wormhole's natural tendency to implode, stabilizing its throat long enough for matter or even a spacecraft to traverse it. The mechanism hinges on something called the Casimir effect, where magnetic fluctuations in a confined space create regions of negative energy. In theory, carefully configured magnetic fields could amplify this effect around a wormhole's neck, acting like cosmic scaffolding to prevent collapse. The Einstein-Rosen bridge, relativity's original wormhole solution, never accounted for such stabilization. But modern extensions of the idea, like those proposed by physicist Kip Thorne, incorporate exotic matter or energy to keep the throat navigable. Magnetized plasma, superheated and spinning at relativistic speeds, could theoretically twist spacetime in ways that reinforce the wormhole's structure. Picture a tornado of magnetized particles orbiting the tunnel's interior, their collective energy warping the fabric of space to maintain equilibrium. Simulations of magnetohydrodynamics in curved spacetime hint at this possibility, showing how certain magnetic configurations might resist gravitational collapse. Interstellar implications are staggering. A stabilized magneto-wormhole could render galactic travel instantaneous from a traveler's perspective, even if the endpoints are light years apart. Of course, the energy requirements border on the absurd, harnessing the output of a neutron star's magnetic field, or manipulating quantum vacuum states beyond current technology. Yet nature might already have shortcuts in place. Some theorists speculate that primordial magnetic fields from the Big Bang could have left behind microscopic wormholes woven into spacetime's fabric, their stability locked in by fluctuations we've yet to detect. The wildest twist, magnetic wormholes might not just connect space, they could bridge time. Certain solutions to Einstein's equations allow for closed time-like curves when magnetic torsion is introduced, meaning a properly tuned field might enable travel to the past or future. Before you dream of time machines, though, consider the paradoxes. Even if such wormholes exist, their magnetic stabilization would require precision beyond anything known to physics, with field strength so intense they'd rip atoms apart at the seams. While experimental evidence remains elusive, projects like the Laser Interferometer Space Antenna could someday detect gravitational echoes from wormholes, perhaps revealing their magnetic fingerprints. Until then, these cosmic tunnels remain a dazzling intersection of relativity, quantum theory, and magnetism's untapped potential. One thing's certain, if wormholes are ever traversable, magnetism won't just be along for the ride, it'll be the invisible architect holding the door open. Galaxy clusters are the universe's heavyweight champions, colossal cities of hundreds or even thousands of galaxies bound together by gravity. But when these titans collide, something extraordinary happens. Their merging doesn't just send gravitational ripples through space-time, it ignites magnetic fireworks visible across the cosmos. Take the Bullet Cluster, one of the most spectacular collisions ever observed. This cosmic train wreck, located nearly 4 billion light-years away, shows two galaxy clusters plowing through one another at millions of miles per hour. The aftermath, a visible shock front sculpted entirely by magnetism, a cosmic tsunami of energy that reveals just how deeply magnetic fields are woven into the universe's largest structures. What makes the Bullet Cluster so special isn't just the sheer violence of the collision. It's the way magnetism leaves a visible scar. As the clusters slam together, their galaxies' mostly empty space between stars passed right through one another like ghosts. But the superheated gas filling the space between those galaxies couldn't slip past so easily. Instead, it piled up in a vast, bow-shaped shockwave like water pushed ahead of a speeding ship. And here's where magnetism steps in. Telescopes like the Chandra X-ray Observatory detected something startling. The gas in that shockwave wasn't just hot, it was fluorescing with synchrotron radiation, the telltale glow of electrons spiraling around magnetic field lines at nearly the speed of light. Those magnetic fields didn't just passively watch the collision, they actively shaped it. Simulations show that as the gas compressed in the shock front, its embedded magnetic fields amplified dramatically, like rubber bands stretched to their breaking point. The result, a visible magnetic wall, a cosmic barrier where the field strength jumps by a factor of 10 in just a few 100,000 light-years. This isn't just a curiosity, it's proof that galaxy clusters aren't just bound by gravity. They're permeated with vast, dynamic magnetic webs that react violently to cosmic upheaval, channeling energy in ways we're only beginning to understand. The Bullet Cluster's shock front isn't alone. Other merging clusters like MAX J0717.5 plus 3745 show similar magnetic fingerprints. In some cases, the collision rips the magnetic fields into vast, rope-like filaments, stretching millions of light-years structures so large they could wrap around our Milky Way 100 times over. These cosmic cables aren't just debris, they're accelerators boosting particles to energies that make Earth's most powerful colliders look like toys. But the real surprise came when astronomers looked beyond the visible shock waves. Using radio telescopes, they detected faint, diffuse emission far from the collision's epicenter, traces of particles accelerated by turbulence in the cluster's magnetized aftermath. It's as if the entire merger site is a giant magnetic mixer, stirring the cosmic pot for hundreds of millions of years after the initial crash. This lingering magnetism might explain one of astrophysics' biggest puzzles: why the space between galaxies in clusters isn't dark and cold, but instead glows faintly with radio light. The answer: magnetic fields energized by ancient collisions are still at work, whispering their presence across the eons. What's truly humbling is the scale of these magnetic dramas. A single cluster merger can unleash more energy than a trillion supernova, with magnetism directing much of that fury. Yet without specialized telescopes, we'd never know it was there, a reminder that the universe's most powerful forces often hide in plain sight, waiting for us to learn how to see them. So the next time you gaze at a Hubble image of a serene galaxy cluster, remember, beneath that calm facade, magnetic tempests are raging, shaping the cosmos in ways we've only just begun to decipher. We've journeyed through 29 astonishing ways magnetic fields shape the cosmos, from birthing stars to bending spacetime, from sculpting galaxies to sparking life's chemistry. Yet here's the humbling truth: everything we've discovered so far represents less than 1% of the universe's magnetic tapestry, the remaining 99%. A vast, uncharted frontier where magnetism could be hiding revelations that rewrite physics itself. Consider this: we've mapped Earth's magnetic field in exquisite detail, traced the sun's turbulent magnetism, even glimpsed fields tangled around black holes. But zoom out to the cosmic web, the filaments of gas and dark matter connecting galaxy clusters, and our knowledge dissolves into guesswork. These intergalactic voids might harbor magnetic fields spanning hundreds of millions of light years, so faint they're virtually invisible to current telescopes. What colossal structures or unseen forces could they reveal? That's where missions like ESA's JUICE come in. Slated to arrive at Jupiter in 2031, this spacecraft won't just study the gas giant, it'll plunge into the magnetic maelstrom surrounding its icy moon. Europa, Ganymede, and Callisto aren't frozen wastelands. They're worlds with subsurface oceans, their hidden waters churning beneath shells of ice. But here's the magnetic twist. These moons don't just passively orbit Jupiter. They generate their own secondary magnetic fields as they move through the planet's colossal magnetosphere. JUICE sensors will detect these subtle electromagnetic whispers, peeling back the ice to reveal whether these alien seas could host life. Ganymede, the solar system's largest moon, is especially magnetic. It's the only moon known to possess its own intrinsic magnetic field, a mini planetary dynamo buried beneath its icy crust. When JUICE measures how this field interacts with Jupiter's, it could uncover secrets about the moon's internal ocean's depth, salinity, even its potential hydrothermal vents. Imagine magnetism as a key to unlocking alien ecosystems, but Jupiter's moons are just the beginning. Future missions aim to probe Saturn's enigmatic moon Titan, where methane rivers might carve channels through magnetically charged organic sludge. Others will study Uranus' bizarre, tilted magnetic field, a cosmic mystery since Voyager 2's flyby in 1986. Each of these worlds offers a new piece of the puzzle, showing how magnetism operates under conditions we can't replicate on Earth. Back on the galactic scale, projects like the Square Kilometre Array radio telescope promise to revolutionize our magnetic mapmaking. With thousands of antennas spanning continents, this behemoth will detect the faintest magnetic whispers from the early universe, potentially uncovering fields forged in the Big Bang's first moments. Other instruments like NASA's upcoming SPHEREX will scan the sky for polarized light, a subtle fingerprint of magnetism's role in shaping cosmic dust clouds where new planets form. Yet for all our technology, some magnetic mysteries may remain forever beyond our grasp. Could there be entire dimensions where magnetism operates by different rules? Do magnetic monopoles, those elusive single-poled particles, lurk in the voids between galaxies, waiting to rewrite quantum theory? The questions outnumber the answers, and that's the thrill of it. Every time we think we've decoded magnetism's cosmic language, the universe throws us a curveball, a magnetar's inexplicable flare, a galaxy with field lines pointing the wrong way, a neutrino that zigged when it should have zagged. So as we stand at the edge of this magnetic frontier, one thing's certain: the cosmos isn't just held together by gravity. It's humming with invisible forces, whispering secrets we've only begun to hear. Whether those whispers lead us to new physics, alien oceans, or something beyond our wildest imagination, well, that's the great cosmic unknown, and it's waiting. From the birth of stars guided by magnetic scaffolding to the invisible highways connecting galaxies across cosmic voids, we've witnessed how magnetism shapes the universe in 30 astonishing ways, each more extraordinary than the last. These fields sculpt planets, ignite celestial light shows, and even whisper secrets about dark matter. Yet for every mystery solved, like the colossal jets of black holes or the eerie precision of pulsars, 100 more remain hidden in the magnetic shadows. Consider this: we've mapped only a fraction of the Milky Way's magnetic web. Beyond our galaxy, filaments of unseen force may stretch billions of light years, their origins lost in the chaos of the Big Bang. We've yet to decipher why Uranus' magnetic field tilts like a drunken top, or how magnetotactic bacteria evolved to harness Earth's magnetism billions of years before humans invented the compass. Even the humble fridge magnet holds quantum mysteries. Why do magnetic poles always come in pairs? Could monopoles lurk in cosmic strings, remnants of the universe's first moments? The tools to uncover these secrets are already rising. The square-kilometer array will scan the sky for magnetic whispers from the cosmic dawn, while quantum sensors aboard spacecraft like JUICE probe alien oceans for electromagnetic echoes of life. Every discovery rewrites the rules. When astronomers recently spotted a galaxy with magnetic fields defying all models, it hinted at forces we've yet to name. So as we reflect on these 30 cosmic transformations, remember, magnetism isn't just a facet of the universe, it's one of its fundamental languages. And just as Carl Sagan once said, somewhere, something incredible is waiting to be known. Perhaps it's a magnetic anomaly rewriting physics, or an alien ecosystem tuned to the hum of a magnetar. Whatever it is, the cosmos is humming with possibilities if only we learn to listen. Visual, a slow zoom out from Earth's auroras to the Milky Way's magnetic filaments, then into the cosmic web's glowing threads, fading to black as Sagan's words